Hello and welcome to the series of lecture on operating system. In this lecture we will learn about deadlocks. The system model is characterized as follows. System consists of resources. Resource types are specified with respect to the terminology R1, R2, Rm. Resources can be either a CPU cycle, memory space or IO devices. Each resource type Ri has Wi instances. So many number of instances can be there for each type of resources. Instances means number of copies. Each process utilizes a resource as follows. So whenever a process requests for a resource or it needs to utilize for a resource, it should request for a resource first, use the resource and release the resource. So this is the corresponding characterization of system model for the deadlock. Now, what is the corresponding important 4 conditions for the deadlock to occur? Okay, first condition is mutual exclusion. Only one process at a time can use a resource. Deadlock can arise if 4 conditions hold simultaneously. All these 4 conditions should be held simultaneously. The first condition is mutual exclusion. Only one process at a time can use a resource. Hold and wait. The second condition is hold and wait. A process holding at least one resource is waiting to acquire additional resource held by other process. So hold means one process is holding a resource. Okay, it is requesting for another resource, but that resource is already held by another process. No preemption. Third condition is no preemption. A resource can be released only voluntarily by the process holding it, after that process has completed its task. So, if a resource has been already given to a particular process, it cannot be forcefully taken away. That is called as no preemption. Circular wait. There exists a set of processes P0, P1 up to Pn of waiting processes such that P0 is waiting for a resource that is held by P1, P1 is waiting for a resource that is held by P2. Similarly, Pn minus 1 is waiting for a resource that is held by Pn. So here there is a circular wait that is created, causing a particular set of process to be in deadlock state. So if a deadlock should occur, all these 4 conditions must simultaneously be available. Mutual exclusion, hold and wait, no preemption and circular wait. So deadlock can occur in mutex locks. So mutex locks already it is a process synchronization tool, right? So deadlocks can occur via system calls or locking, etc. Okay. Now we will learn about the resource allocation graph to understand the deadlock in more detail. Now a set of vertices V and set of edges E. Resource allocation graph is characterized by set of vertices V and set of edges E. V is partitioned into 2 types, that is processes, set of processes P1, P2, Pn in the system. Similarly, another is R, where R is a set of resources in the system. The request edge is a direct edge where PA is requesting for RJ, that is the corresponding edge is towards a resource, from process towards resource, that is called as resource request edge. Assignment edge, a directed edge from R to P, from a resource R to process P, then it is called as already that resource has been held by that process. So this is the typical sequence of thing we need to, that is terminology we need to understand for constructing a resource allocation graph. Processes in the resource allocation graph are represented as circles. Resources with a several number of instances are represented as squares. Okay, here this one with square, and inside also small 4 squares are there, which represents that 4 instances of a particular resource type. That is 4 copies of the same resource type is available. PI request instance of RJ means from process to PI to RJ there is a direct edge. So if PI holding a resource means there is a edge from R to P. So this is called as assigned edge. Already PI is holding a particular resource RJ. So if you see here the typical example here, So P1, P2, P3 are processes are represented in circles. Okay. R1, R2, R3 and R4 are resources, and the resource instances, number of instances are represented as dots. For example, if you see R1 as a single dot, which means only one instance of R1 is available. If you see R4, there are 3 dots, which means that number of R4 available is 3. Okay, number of copies of R4 is our instances available is 3. Now, with respect to the terminology in the previous slide, what is that? From R2 to P1, there is an edge, which means P1 is already holding R2, one instance of R2. Okay, but P1 is requesting one instance of R1, that is edge from P1 to R1. Similarly, when you consider P2, there is an edge from R1 to P2, which means P2 is holding R1. There is an edge from R2 to P2, which means that P2 is requesting R2. P2 is again holding R2. Okay, P2 is holding both R1 and R2. Okay. Similarly, there is a direct edge from P2 to R3, which means P2 is requesting R3. And finally, there is one edge from R3 to P3, which signifies that P3 is holding R3. Okay, so this is way with which the resource allocation graph can be analyzed. Now, this is an example resource allocation graph with a deadlock. So, what happens? See here, P1 is holding R2, one instance of R2. P2 is holding one instance of R2. Okay, two instances of R2 is available. That is held by both P1 and P2. Right? P1 is requesting R1, which is held by P2. Right? Similarly, P2 is requesting R3, but R3 is acquired by P3 already, and P3 is requesting R2. But two instances of R2 already available, but those two instances are held by P1 and P2. Now there is a cycle, that is P1, R1, R1, P2, P2, R3, R3, P3, and then P3, R2. So starting from R2, R2 to P1, P2 to R1, P1 to R1, R1 to P2, P2 to R3, R3 to P3, P3 to R2. The cycle occurs. So this condition we call it as a deadlock. So with the resource allocation graph itself, okay, we can identify whether there is a deadlock or not. So this example, a graph with a cycle but no deadlock. So there is a cycle, but there will be no deadlock in this example. So we see here, start with the P1. So P1 to R1, R1 to P2 is there, and similarly R1 to P3 is also there, P3 to R2, R2 to P1, P1 to R2 to P4. There is a cycle, but there is no deadlock. So there is basic facts we need to understand here. If graph contains no cycles, there is no deadlock. Okay, so there is a no cycle means there is no deadlock. If a graph contains a cycle, if only one instance per resource type are available, then there is a deadlock. Okay, so only one instance are there, then definitely there is a deadlock with a cycle. If several instances per resource type are there, possibility of deadlock. Deadlock may occur but might not be occur. Both conditions are there. So if there are no cycle, no deadlock. Definitely there is no deadlock. If there is a cycle and if there is a one instance per resource type, definitely there will be a deadlock. If there are more instances, like our previous example, if you see here, R1 has two instances, R2 has two instances. Even though there is a cycle here, but no deadlock, because R1 and R2 are having two instances. That two instances are satisfied the request made by P1, P2, P3 and P4. So even though there is a cycle, because of more instances of R1 and R2, which could satisfy the request of P1, P2, P3, P4. So there is no deadlock. But not all cases might be like before example, but even though there are multiple instances of resource type, there may be possibility of deadlock. Now, what are all the methods of handling deadlock? So, ensure that system will never enter a deadlock state. So, before the occurrence itself, we are checking. Okay, so meaning a mechanism. So that is called as deadlock prevention, and the second one we call it as deadlock avoidance. Allow the system to enter a deadlock state and then recover. Okay, so ignore the problem and pretend that deadlock never occur in the system. Okay, this technique is used by modern operating system, Unix operating system. Deadlock prevention. So what is the deadlock prevention? What is the condition for deadlock to occur? All the four conditions should be satisfied: mutual exclusion, hold and wait, no preemption, circular. Now we are going to negate any one of the condition. If you negate any one of the condition, then we are preventing from the deadlock. What is mutual exclusion? Not required for shareable resources. Okay, so if you negate the mutual exclusion condition, then deadlock never will happen. Hold and wait must guarantee that whenever a process requests a resource, it does not hold away any other resource. So if we guarantee that, then no deadlock will happen. Okay, that is, a process requesting for a resource should release its resource either previously it has acquired. So that is the meaning of negating the hold and wait. No preemption. If a process that is holding some resource requests another resource that cannot be immediately allocated to it, then all resources currently being held are released. Okay, so no preemption means the corresponding process requesting for some resource, but that request cannot be granted immediately. So whatever the resources that particular process is already there, it releases it. So we are negating the no preemption condition. The preempted resources are added to the list of resources for which the process is waiting. Okay. Circular wait. Impose a total ordering of all resource types and require that each process requests resource in an increasing order of enumeration. So in this way, we can negate the four possible conditions, simultaneous conditions. Any one of the conditions can be negated so that we can prevent the deadlock from happening. So in the next subsequent lectures, we will learn about deadlock avoidance, deadlock detection and deadlock recovery. Thank you.